Okay, I want to dig a little bit deeper into Newton's second law and net force and understanding what net force is. And I'm going to use the example of the coins that were flying across the table during the law of inertia demonstration. And there's some things that I'm not going to get into too much detail on with this video. It's just going to have to be accepted as it is, and I'll post some resources to explain why these things were set up that way. Also, if it's any comfort, this is a concept I didn't understand until I was sitting in front of a test in College Physics 1. So, looking at this, we're going to break it down into three pieces. We're going to look at the coin before it was hit by the knife, while it was hit by the knife, and then after it was hit by the knife. So, looking at the before situation. Before situation, we have a coin that's sitting on a table, and we have a contact force of the table pushing up on the coin. We have a contact force by the coins that is pushing down, and we also have what right now I'm labeling as gravity. Later on, in different examples that I might give, this will be labeled as weight. So everything here has to be balanced because this object is at rest and forces must be balanced. I've shown this on this diagram here by the fact that 1, 2, 3, 4, 5, 6. I have 6 squares for the length of the arrow going up, and I have 1, 2 for gravity going down, and I have 1, 2, 3, 4 for the force of the chain or force of coins going down. And when we add these up, of 2 plus 4, that equals 6. So we have the 6 going up equaling the 6 going down. So things are balanced. Now, normally, and going forward from this point, we aren't going to use the words up and down. We are going to use positive and negatives. So on this diagram, I would say that maybe up is positive and down is negative. So this would now become a -2. This would become a -4. And this doesn't change this right here, because here in physics, +6 is going to equal the -6 going down. And I know that in math and in integers, this would not be true, but really this right here is telling us a direction. It's replacing the words up and down. So 6 equals 6 is still true. Just, that's one thing I would caution you on, is realizing that while we may use the law of integers going forward, there are some cases in which we have to throw this idea of what integers are out the window and recognize this positive and negative as a direction. So balanced forces, Newton's first law holds up. An object at rest remains at rest because everything is balanced acting on the coin. So I'm going to pause the video here and set this up for while the coin is being hit. Okay, now let's look at the coin while it is being hit by the knife. While it is being hit by the knife, I have a force by the knife going this way, and I have some friction force that is opposing it going this direction. Now these forces are imbalanced. I have 1, 2, 3, 4 going to the right, and I have 1, 2 newtons going to the left, and 4 to the right does not equal 2 to the left. If I go back to the idea of using positive and negatives to show direction, +4 does not equal -2. So this is a case where we have unbalanced forces, and we can use this right here to find the net force. And here's the second definition of net force. With net force being the sum of the forces in one direction, I can take and find the net force by saying +4 plus -2 newtons is going to equal +2 newtons. So right here, this that I just did is the net force. And this +2 newtons tells me that my net force is going this direction. And my net force will always point in the same direction as acceleration, so this also has an acceleration going this way as well. I'll just go ahead and put it up here. So my net force is this direction, my acceleration is this direction, and to be accurate with my net force is going to be 1, 2, just like that. So this is the situation of while the coin is being hit. How big this is, I don't know. For the acceleration, I'd have to do the math and weigh the coin. So I'm going to pause here and set it up for the after. Okay, after. Okay, so this is the after while the coin is still on the table and sliding across the table. I have the force of the table still pushing up, I still have gravity pulling down, and I still have friction by between the coin and the surface of the table. And if we look here, it's very clear here that we don't have any balance forces. We have nothing pushing this way, but we have friction still acting this way with -2 newtons. And using the idea that the sum of the forces in one direction equals the net force, 0 newtons in the positive direction plus -2 newtons equals net force. I have -2 newtons equaling the net force. So net force will then be pointing this direction. And my acceleration will also be in this direction, with how big that is unknown until I weigh the coin and do the math from there. So forces here are still balanced up and down. Side to side here we have unbalanced forces. We have the net force going this direction. We have acceleration also going this direction to the left, but our coin is still traveling to the right. And this means, in this case, we have a situation where the coin is slowing down as it slides across the table.